Hello everyone, welcome to CSEN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mogi. Um, Last lecture we started our introduction into communication networks. We saw an overview of what the internet looks like. We said that it is actually made of an edge and a core, and the edge is where our devices reside. And in the core, we find switching devices such as switches and routers, and everything is connected using communication links. And we have access networks that enable us to insert our packets or inject our packets from the edge into the core. And we started looking into the different types of access networks. We started actually with dial-up modem, and then we discussed digital subscriber lines and cable modems. And after that, we discussed wireless networks, particularly first we discussed institutional networks and then wireless networks, particularly Wi-Fi and cellular or mobile networks. And finally, we discussed home networks as well, Wi-Fi routers. Okay. In today's lecture, we're going to start by looking at the core. We're going to start by opening up this black box that we said contains just switching devices, mainly switches and routers, and see how it works. So basically, the job of the core is to transport packets from one place to the other, is to take the packets from the access networks, send them across several routers. So one router sends it to another router, sends it to another router, according to a certain path. And then finally, it reaches a final access network that gives this packet to the destination. So let's say, for example, you're sending a WhatsApp message. You type the message and click send. The access network in this case is either your Wi-Fi network at home or the mobile network. It gets injected into the internet core, and then it gets routed to a WhatsApp server. The WhatsApp server is typically connected, for example, using an institutional network. It's connected to a switch or something like that, and it receives the message from that switch and then forwards it to another client in the reverse direction. Now, the network core just consists of routers, and it's the job of something called the routing protocol to find a path through the network core, to find actually the set of routers that are going to transport the packet from source to destination. We'll discuss actually routing protocols later, but today we want to discuss how the network core works. The focus of our discussion is going to be how resources are shared. Because when you think about it, the network core is basically just a huge shared resource. All these routers are not just used actually by one person or one institution. They are actually shared among all internet users around the world. And so if I have a client and the client wishes to send a packet of data to a destination, and the packet is going to jump over several routers until it reaches the destination. These routers are not dedicated to just this communication session. They are actually shared. There is another client that is maybe connected to this router. There is another client here. There is another client there. And so these three routers in this case are a shared resource. How are they going to be used between all the clients that are connected to them? How is the network core how is the network core shared among all the internet users around the world? Before we actually discuss the internet in particular, let's actually just think about this challenge. How do we share the resources of a shared device? Okay. There are mainly two ways to share these resources. The first one is called circuit switching, and the second one is called packet switching. Circuit switching is quite simply, if you have a resource, you divide it among the users that would like actually to access this resource. So for example, if you have a router and you are actually trying to share the resources of that router among several devices, what you can do is that you reserve some of the resources of that router for one connection and reserve another part of the resources of that router to a different connection. So let's take, for example, this router. This router now has two communication sessions going through it, the blue one and the red one. Okay, so it has to figure out a way how these two communication sessions will exist simultaneously over the router, meaning how will the packets belonging to these communication sessions be transferred over the router. Okay. In circuit switching, there will be a part of the resources of the router, the transmission resources and the computing resources. Part of them will be reserved for the blue connection. Part of them will be reserved for the red connection. And so this is how circuit switching works. It works by resource reservation, which means that before you can actually use the shared resource, you have to reserve the resources themselves. Okay, this is why we call it circuit switching, because once the resources are reserved, they belong to you. No one else actually shares them. No one else can use them until you release the call. Actually, landline telephone networks and even mobile networks, they work in this way. Once you actually make a call, and if the network has sufficient resources for this call, the resources will be reserved in the network for this call. And these resources will not be released until you hang up the call, meaning that the resources will belong to you. They are reserved to you for the entire duration of the call. So the disadvantage here is that there is something called the call setup time. You have to set up the call. You have to reserve resources. Your device has to basically negotiate with the network the resources that need to be reserved. If the path, for example, let's take here the red connection. If the path is over 1, 2, 3, 4, 5, 6 routers, the call setup will make sure that there are resources reserved over all the 6 routers. So essentially, all the 6 routers will actually have to have some empty resources available. And if they do, then these resources will be reserved for this connection. If resources are not available, if the entire network is congested and there is no sufficient resources for this call, then the call has to be rejected. It cannot actually be led through because it is pointless in this case. If you let the call through, then there will be no resources to carry its data. And so it will fail. Okay. So the advantages of circuit switching is that you have reserved resources, and so there is no interference. You may or may not get the resources depending on their availability, but if you get the resources, no one else shares them with you. And so there are actually two main ways how to share the resources of a router using circuit switching. They are called frequency division multiplexing and time division multiplexing. Basically, you either divide the resources in time or in frequency. Let's take time division multiplexing first. Let's say you have 4 communication sessions trying to actually share the resources of the same device. What you can do is that you can divide the time into fixed slots. The slots can be of any duration, for example, 1 second or 1 millisecond or whatever. And then you assign each slot to a particular communication session. So for example, here, this is session 1. This is session 2, this is session 3, this is session 4. So each of the 4 communication sessions will get 1 slot. During this slot, the end users may actually send data to each other, meaning that if someone actually has a packet to send, it can only be sent during that reserved slot. Okay? If a packet is generated outside of that slot, it has to wait its turn. So the first time slot goes to session 1, second time slot goes to 2, third time slot goes to 3, fourth time slot goes to 4, and then it repeats. 1 gets to transmit again, then 2, then 3, then 4, and then 1, 2, 3, 4, and so on. Okay. So devices can only send, or the router can only send the data in the dedicated slot, but the slots repeat. Okay. So in this case, the resources are shared evenly among all the communication sessions that are requesting access to that resource. In frequency division multiplexing, you share bandwidth. This is actually the same as what happens in the radio and television channels. For example, when you tune your radio to a particular station, okay, you tune it to the frequency of that station. And so in that specific frequency, when you tune your radio to that frequency, you are expecting to get only that station. It is not possible that you would get another station, because that station has purchased this frequency and has reserved this frequency for its broadcast. Okay? This is frequency division multiplexing. You have the entire spectrum, and you divide it into frequency chunks or frequency bands, and then each communication session gets a frequency band. So in this case, 1 gets this frequency band, 2 gets this one, 3 gets this one, and 4 gets this one. And so because each of them has a frequency band, they get it all the time. So time is no longer divided into slots. The frequency is divided into chunks, and each one gets a chunk of frequency for the entire duration. Again, the resources are shared evenly between all the communication sessions. And you cannot say that using FDM or TDM, one client will actually get more resources in one way or the other. Okay, because in frequency division multiplexing, yes, you get your frequency band for the entire duration, but you get a smaller frequency than that you get with TDM. With TDM, you get to use the full resources of the router, but only during a particular time slot. So in either way, you are getting actually only a portion of the resources. Either you're getting this portion for the entire time, or you are getting the full resources, but only for a small time slot. Okay. Regardless of FDM or TDM, both of them are actually not used in the internet at all, because they suffer actually from a very important disadvantage. Let's say you're actually making a call and your network uses FDM or TDM, using circuit switching basically, and because of that, you have reserved the resources for the call. But let's say once the call is open, the call is active, you are silent for a while. You went, for example, to open the door, okay, or the person you're calling is not saying anything for a while, or whatever happens. During this period, the resources are still reserved to you, even though you're not using them. Okay, so circuit switching tends to be very lossy. It loses actually a lot of resources, and therefore the overall capacity of the network is significantly reduced because of this resource reservation. You cannot actually release the resource until the clients no longer need them, until the clients hang up the call. And so it ends up wasting a lot of resources in this case. This is why the internet uses a different type of resource sharing, which is called packet switching. Packet switching basically means that each packet, once it arrives at the router, it's going to use its full resource. So what happens is every router, let's say this router is connected to actually many devices, it is going to have an internal router, an internal buffer, an internal memory space that is called the queue. Once a packet arrives at the router, it joins the end of the queue. Okay, so it waits for its turn. If the router is connected to many devices, it can actually receive many packets within a small window of each other. And so they might all actually be waiting in the queue. And the router is going to transmit one packet after the other. This is actually what is called packet switching. Now, there are two types of routers that implement packet switching. The most common one is called store and forward, meaning that the router is going to have to receive the entire packet before it begins to transmit it to the next hop or to the destination. Okay, that means when the router receives the packet, it cannot actually start transmitting it until it receives every bit in that packet. There is another type of router that is called cut-through. Cut-through routers do not have to wait until the full packet is received. They can actually start transmitting the packet until or after the first few bytes have been received. Once it actually knows the address of the destination and how it is going to forward the packet, it can start transmitting the packet before the remaining bits are delivered. Once the remaining bits are delivered, it's going to continue delivering them. Each one has actually its advantages and disadvantages. I'll not go into them now, but store and forward is the more common type of router in this case. Now, we said that the router will have a memory space called a buffer where the packets are actually saved until they get its turn to be transmitted. Now, because it's a memory space, this essentially means that it will have a fixed capacity. There is nothing as an infinite amount of memory. And so because it has a fixed capacity, there is a chance that it will be filled. That means packets are arriving to the router at actually a very high rate, faster than the router can transmit. And so incoming packets will keep joining the queue. The queue will become longer and longer until it becomes completely full, until the memory space is completely consumed. So there is no more space for incoming packets. So what will the router do? If it receives more packets, it will have no choice but to drop them, to throw them away. That means this packet will have to be transmitted, retransmitted at some point. The router will actually lose it. Okay, this event is called congestion. This is when the queue is full and the router starts to actually drop packets. This is actually the case with packet switching. What it essentially means is that there is no guarantee for resources. That means if this is the router and if this is the queue, at any given time, you do not know who is sending packets to the router. If only one device is sending packets to the router, then it is going to use the full capacity of the router and it is not going to compete with anyone else. If another device starts to actually send packets to the router, then the two of them are going to be competing for the resources of the router by actually joining the queue in this case. In either case, the resources that you get depends on what other people are transmitting as well. This is actually, if you remember the discussion from last lecture, we said that the internet is best effort. It cannot give you guarantees on delay or any performance metric. It cannot give you guarantee that the packet will actually be delivered. This is actually why. You cannot give a guarantee on delay because at the end of the day, the routers are going to be the ones responsible for forwarding the data. And the routers do not know when other people are going to transmit. So they cannot tell you, I'm going to give you this amount of megabits per second at this time. Because if it can give you this guarantee, then it would actually be reserving resources and it would be doing circuit switching. Packet switching is not that. You get the resources as they are available. If you are the only one sending to the router, then you're getting the full resources of the router. If someone else is sending, then you have to share the resources of the router with that other device. Okay. So when you are on a Zoom call or whatever voice over IP call, and you suddenly find your voice not being heard by everyone else, you know that most probably the packets carrying your voice are lost somewhere in the network. That means there is a router, for example, that is actually dropping the packets carrying your voice. Packet switching is also sometimes called statistical multiplexing. You see here actually how the packets from devices A and B are queued inside the router and they are transmitted actually one by one over the external link. Let's take a numerical example to see how a store and forward switch would work. Let's say this device, let's call it device A, is sending a packet to device B. We would like actually to calculate the overall delay until the packet reaches B. And so what will happen is that A will first transmit the packet to the first router, and then the router, because it's store and forward, will have to receive the packet fully. And after it is received fully, it will start forwarding to the second router. And then the second router will also have to receive it fully before it starts forwarding to the destination B. And so each one of these devices will have a certain speed. Let's say all the devices have speed R megabits per second. So we want to calculate the overall delay from A to B. And so we want to calculate the delay components over each hop or each step. So starting at device A, how long will it take it to push the packet to the first router? If the packet has length L bits, okay, and the speed of the device is R megabits per second, it will take L over R for A to push all the bits of the packet. Because A has a certain speed, what it will do is it will take the packet, which is composed of ones and zeros, and it will convert every one and every zero to an electrical signal. This is not a process that takes zero time. It takes a little bit of a delay. This delay is actually the transmission rate of the device, which we are assuming to be R megabits per second. R megabits per second means that device A can actually transmit R megabits every second on the wire. Okay, that means when it receives the packet, it's going to transmit this packet one bit after the other until it finishes all the bits in that packet. So once the packet reaches the first router is going to do the same. It's going to convert the electrical signals into, the bits into electrical signals. And so this also will take L over R and then send to the second router, which is going to take another L over R, and then it is received at B. So we have L over R at A, L over R at the first router, and L over R at the second router, giving us a total delay of 3L over R in this case. Another example just to show you how packet switching significantly improves the capacity of the network over circuit switching. Let's say you have this scenario. You have a 1 megabits per second router that is shared among n users. And so if you have 1 megabits per second, then you have n users, and each user is going to consume 100 kilobits per second when active, then you are going to end up with 10 users no matter what. Even if the users are active only 10% of the time, in circuit switching, it doesn't actually make a difference because the resources of the router are going to be shared evenly among the n users for the entire time until one of them releases the resources. And so it makes no difference whether the users are silent some of the time or they are active 100% of the time. In circuit switching, you can only support 10 users. In packet switching, using combinatorics, you can actually calculate that the probability that you have 10 active users at the same time is less than 0.004. So you can actually support over 35 users. That's over 3 times as many users as you have with circuit switching. Why? Because we assume that the users are active only 10% of the time. Okay? So you can see clearly that packet switching significantly improves the capacity of the network. Okay? This is actually why it is used in the internet, because it's a global network. Obviously, you want to support a larger number of devices, and you also don't want to go through the hassle of call setup. And one primary reason why we are using packet switching is that we don't know when people will actually require the resources of the network. Circuit switching would be a fantastic idea if the traffic was deterministic. If you know exactly who is going to send packets and at what time, then you can actually create a schedule where everyone can transmit when they are actually generating packets. But the problem is in the internet, you never know that. You never know who is going to transmit and at which time. So we say that actually the traffic over the internet is bursty in nature. That means you open, for example, Facebook, so you're getting a burst of data. You're actually getting some packets at this time, and then you stay silent. You put your phone aside and you're no longer using the internet at this time. Okay. So all traffic on the internet is like that. There is a burst of traffic, and then things stay silent. And the time at which this burst is going to be created is random. You don't actually know when it will happen, which is why packet switching at the end of the day significantly improves the capacity of the network. With this discussion, we now understand how the internet is actually structured. We know the edge and the core. We know what we find in the edge. We know access networks that connect the edge to the core. And we know how the core works. We know an overview of basically how the core shares its resources, and we know how packet switching works. Now, to continue our discussion of the core, so far we have assumed that it is just a black box consisting of switching devices that are actually sending data to each other. Let us now see how this black box, how this core is actually organized. In the internet, the core is actually consisting of a hierarchical structure. Okay, that means not all the networks in the internet are on the same level. First of all, there is no single core. There is actually a large number of connected networks. This is actually what the internet means. It's an interconnection of networks. These networks are owned by different companies. Some of them, we call them internet service providers. These are the ones that sell internet connectivity to other companies or to people. These internet service providers have actually different levels in the hierarchy. At the very top of the hierarchy, you have what is called a tier 1 ISP. Tier 1 is actually the largest network, and its job is not to actually sell connectivity to customers. Its job is actually to connect continents. So, for example, you have Europe and you have North America. You have a tier 1 ISP connecting these two continents, most likely using an underwater submarine cable or something like that. Okay? Similar to actually what you see in this figure. This is just an example of a number of submarine cables connecting Europe to the United States and Canada. Okay, so these tier 1 networks, they own these large networks that connect continents. Below them, you have the second level of the hierarchy, which is called the Tier 2 ISP. The Tier 2 ISP get their connectivity from a Tier 1 ISP. That means they are actually a customer of a Tier 1 ISP. The coverage range of a Tier 2 ISP is typically smaller. So we're talking about either a country or maximum a continent or something like that. Okay, so it doesn't have global reach. Okay, and it gets its connectivity from a Tier 1 ISP. What do we mean by gets its connectivity from a Tier 1 ISP? If the packet is going from a device in a Tier 2 ISP to a device in the same Tier 2 ISP, then it doesn't actually need to exit this ISP. But if you want to go outside this Tier 2 ISP to another one, then you either jump from a Tier 2 to another Tier 2 directly, or you go through a Tier 1 ISP, and then it connects you to the other Tier 2 ISP that you want to reach. Okay? This is the importance actually of Tier 1, because at the end of the day, there is no one above them in the hierarchy. They are the ones that connect all the continents to each other. And so at the end, if you don't have a path to the destination, you are going actually through a Tier 1 ISP. And the final level of the hierarchy is called Tier 3 ISP, or sometimes it's called local ISP. This is actually the one that we buy access from. Okay? So you are a customer of a Tier 3 ISP. The Tier 3 ISP is a customer of a Tier 2 ISP, and the Tier 2 ISP is a customer of Tier 1. And all the Tier 1 ISPs are peers of each other. So they are all connected to each other, so they can at the end of the day, provide global connectivity. So in Egypt, we have several Tier 3 ISPs. We have, for example, Orange, we have Vodafone, we have Etisalat, we have TE Data. All of these are Tier 3 ISPs, and they all are customers of one Tier 2 ISP that we have in Egypt, which is Telecom Egypt. So in this case, Telecom Egypt has or owns a Tier 3 ISP, which is TE Data, and itself owns also a Tier 2 ISP. There is no problem there. The entity or the network that consists of the Tier 2 ISP will not actually sell connectivity directly to customer. It is actually its arm or its branch, which is TE Data. That's the Tier 3 ISP that actually sells connectivity to customers. So one organization can own both the Tier 3 ISP and the Tier 2 ISP as well. Sometimes they also own a Tier 1, but this is not very common. The thing you have to know about all these levels of the hierarchy is that no one actually is responsible for assigning them. No one is responsible for telling an ISP, you are actually Tier 2, or you are Tier 1, or you are Tier 3. It is actually by their functionality. If their functionality is to connect continents and they are peers of all Tier 1 ISPs, then it is a Tier 1 ISP. If it has a smaller scope but doesn't still send connectivity directly to customers, then it is Tier 2. If it sells connectivity to customers, then it is a Tier 3. So at the end of the day, once you actually send your packet, you inject it into a Tier 3 ISP, and then if the Tier 3 ISP cannot deliver directly, then it sends it to the Tier 2 ISP that it is a customer of. If it cannot still deliver it directly, then it sends it through a Tier 1. The Tier 1s are peers of each other, so it can jump from a Tier 1 ISP to another Tier 1, and then the Tier 1 sends it to a Tier 2, and then a local ISP or a Tier 3, which then sends it to the final destination in this case. So your packet may pass through many, many networks before it reaches the destination. Okay. This concludes our discussion of the, let's say, the overview of the internet, the core and the edge. And now we are actually going to move to another introductory topic in networks, which is how to measure network performance. Now that we understand what networks look like, we understand its basic structure, let us now try to actually evaluate their performance. We would like to understand, why is it that when you make a call, sometimes you get good quality and sometimes you get bad quality if it's a voice over IP call? How can we translate this naturally occurring phenomenon to actual network metrics? We have to ask ourselves first, what kind of network metrics do we care to evaluate or do we care to calculate? What are the network metrics that would actually give you a good idea about how the network is performing? There are mainly 4 network metrics that we are primarily interested in. There are others, so there are several other network metrics, but we are particularly interested in this course in these 4 metrics. They are delay, packet loss, and throughput. Sorry, there are only three, not four. So delay, packet loss, and throughput. These are the three metrics that we are going to use to evaluate the performance of a network. And so let us study actually each one by itself. We will start with delay, and after that we will discuss packet loss, because delay and packet loss are somewhat related. So we want to focus on the delay that occurs at a particular router when it sends the packets to the destination. So the router receives the packet. We want to calculate the total delay until the packet reaches the destination. So to calculate the delay, we have to calculate all the components of that delay. And so we have to think about what happens to the packet from the point when it is received at the router until the point when it is received at the destination. So first of all, when a packet is received at the router, what will the router actually do with it? The first thing that the router will do is that it will read parts of that packet that we call the headers. And the headers don't actually contain data in the packet, they contain information as to how to forward the packet. They contain basically addresses. We will discuss this probably in the next lecture, but for now, they actually contain addresses, IP addresses, for example. So the router will have to process this packet, will have to read the headers in order to know how to forward the packet. So this is the first delay component. This is not a zero time or a zero delay process. There is actually a time that is called processing delay. This is the time the router needs to process the packet. Once the packet is processed, it will have to take its turn in the queue. So this is called queuing delay. If the queue is completely empty, then the queuing delay would be zero. If there are other packets that have been received at the router before, then these packets will have to be transmitted in full by the router before the new packet can actually be transmitted. So the queuing delay may be zero, or it may be greater than that. In all cases, this is actually the second delay component. Once the packet reaches the front of the queue, then the router will start to transmit it. Again, this is not a zero delay process. The router will actually transmit it one bit at a time. It will take one bit, convert it to electrical signals, and then send it over the line. Okay. The rate at which the router is capable of transforming bits into electrical signals is called the transmission delay. The transmission delay, as we calculated it, it's equal to L over R. L is the length of the packet, and R is the rate of the router. The rate of the router is a fixed quantity. Okay, so it's actually a physical capacity of the router. It cannot be exceeded. And L depends on the size of the packet. So it can actually be a variable amount, but if we assume that all packets have the same size, then L will be constant. Now, once the packet is transmitted, it's transmitted as an electrical signal over the wire. So it has to travel over the wire until it reaches the destination. I'm saying wire, but this can also be a wireless link. Even if it's a wireless link, the electromagnetic signal in this case has to actually travel a certain distance until it reaches the destination. This is also not a zero delay process, and this last one is called propagation delay. Let's examine these four delay components and see which of them are constant and which of them might actually change. Processing delay is the time actually that the router needs to read the packet headers or process the packet. This is more or less a constant time, okay? Because it doesn't depend actually on the packet size, because the router doesn't read the entire packet. The router just reads the header, and the header more or less has a fixed size. It can actually change, but it doesn't vary significantly. Transmission delay depends only on the packet size and the transmission rate. If they are both constant, then the transmission delay is also constant. If one of them changes, for example, the packet length changes, then the transmission delay will change as well. The propagation delay depends on two things. Depends on the medium itself. What type of medium is it? Is it a wired medium and is it a wireless medium? For example, if it's a wireless medium, then the electromagnetic signals will travel at a speed of 2 × 10⁻⁸ meters per second, the speed of light. If it is something else, then the speed may actually be slower. There is nothing higher than the speed of light, obviously. Okay, so it depends on the speed at which the signals are propagating, and depends only on the distance it has to travel. Obviously, if a signal has to travel a very short distance, that is, then you'll have a shorter propagation delay or a smaller propagation delay than if the signal has to travel to a satellite, for example, or between continents. This is actually why satellite internet will always suffer from significant delay. When you get satellite internet, you have a significantly abundant bandwidth. The bandwidth is very high, but the delay is also very high because no matter what you do, the signal that you send will have to travel to a satellite and come back. The distance is very large and you cannot shorten it. Okay? So propagation delay may actually play an important role if or may be significant if the distance is very long. The final delay component is queuing delay. Now, queuing delay depends on one main factor, which is actually the traffic. Do we have other people actually sending packets to the router? In this case, the queuing delay will be high. Or am I the only one actually sending packets to the router? In which case, the queuing delay will be small or could even be zero. Okay, so queuing delay is definitely a variable amount. Everything else we can actually say is constant. Propagation delay depends on physical characteristics of the medium as well as the distance. Both of them are actually constant. Processing delay, we said, depends on reading the header, so it's also constant. Transmission delay, if the packet length is constant, then the transmission delay is constant as well. Queuing delay will always be variable because it depends on who is sending at what time, and this is not something that can be controlled, and so queuing delay is always a variable component. We can actually see our discussions here. So we have transmission delay, propagation, queuing, and nodal processing time. And this is basically how things are calculated. So transmission delay is L over R, propagation delay is distance over speed. You have to note here that the speed and the transmission rate are very different quantities. Speed, S, which is actually the factor that you use to calculate the propagation delay, is the property of the physical medium. As we said, if it's a wireless link, then you're traveling at the speed of at the speed of light, okay? 2 times 10 to the power 8 meters per second. If it is a wired link, then the signals may actually be traveling at a smaller speed. This is actually the physical speed of signals traveling over the medium. R is the transmission rate of the router. This is the rate at which the router is capable of transforming bits into electrical signals. It has nothing to do with the physical medium it is connected to. This is actually a property of the router itself. It's a property of the hardware of the router itself. Let's take an example to see the differences between transmission delay and propagation delay. Let's assume we have a caravan, and the caravan consists of 10 cars, as you see here. Okay. The cars line up at a toll booth. Each one has to purchase a ticket, and once they purchase a ticket, they travel over the road. The road has distance of 100 kilometers. So you have 10 cars. The car, once it exits the toll booth, it travels at a distance of travels at a speed of 100 kilometers per hour. And the toll booth will take 12 seconds to service each car. That means it takes around 12 seconds to purchase a ticket and exit the toll booth. Okay. Okay, so we want to calculate how much time it would take for the entire caravan, all the 10 cars, to go actually to the second toll booth. First of all, each car needs 12 seconds to be serviced at the toll booth, and we have 10 cars, so we will need a total of 120 seconds to service the entire caravan. This is actually more or less the transmission delay. You need actually 12 seconds per car. This is actually the speed at which the toll booth is converting a car that is standing in front of it to something that is traveling on the road. This is your transmission delay. Once the car exits the toll booth, it travels over the road, and it travels at a speed of 100 kilometers per hour, and the distance is 100 kilometers. So the propagation delay is actually 1 hour in this case. You have 1 hour or 60 minutes plus 2 minutes or 120 seconds. You have a total delay of 62 minutes for the entire caravan. Okay. These 60 minutes, how much first car only arrives. It would take only 12 seconds plus 1 hour. So 12 seconds to exit the first toll booth, 1 hour to travel to the second toll booth, and that's it. That means after 1 hour and 12 seconds, the second toll booth would start receiving the first car, but there would be more cars coming along the way. Here, you can only see the transmission delay and the propagation delay. The transmission delay is the rate at which the toll booth is pushing out cars. It would be the same as the rate at which a router is pushing out bits, or the rate at which the router is converting bits into electrical signals. And the propagation delay is when the car actually exits the toll booth and travels over the road, or when a bit is converted to an electrical signal and the electrical signal has to propagate until it reaches the second route. Let's change the example a little bit. We are keeping the same number of cars, so 10 cars. Now we're saying that the cars can drive at a speed of 1,000 kilometers per hour once they exit the toll booth, and it will now take 1 full minute to service the car. So we assume that the transmission rate is smaller, or the transmission delay is higher. Instead of 12 seconds, it's now 1 minute. However, the propagation delay is much smaller because the speed is now significantly higher. Instead of 100 kilometers per hour, it is 1,000 kilometers per hour. So if I'm traveling at 1,000 kilometers per hour for a distance of 100 kilometers, I will need only 6 minutes to travel for the entire 100 kilometers. So that means 1 minute to be serviced and 6 minutes to travel. So the first car will actually reach the second toll booth after 7 minutes. After 7 minutes, the first toll booth would have processed 7 cars. So the caravan would have 3 cars remaining. The toll booth would have 3 cars remaining in the caravan. This is a phenomenon that can actually happen in a real network. You have 2 routers. The router can actually transmit the first bit and it can propagate to the second router. And the first bit can actually reach the second router while the first router is still actually pushing bits outside of itself. Okay. This is basically, let's say, the analogy between the transmission delay and the 10 caravans or the toll booth, and the propagation delay and traveling over the road. In any case, the total delay that we have is just the summation of all the delay components as we have seen. Now let's see the relationship between delay and packet loss. So what happens is that the router, as we said, is receiving packets, and the router is typically connected to many devices. Okay? So it's receiving packets and adding them to the queue. And we said that the queue is a variable component. That means that it can increase or decrease depending on how much traffic is being sent to it. And because it's a variable component, it is quite often the deciding factor in the entire delay of the connection. If you are making, for example, a Zoom call, and you're seeing, for example, that your voice is lagging, then you may know that there is actually high queuing delay at a particular route. There is no significant packet loss because packets are still being delivered, because you can still hear your voice, but it's delivered after a significant delay, meaning that there is actually congestion in the network. So let's try to calculate that. We want to calculate a metric that is called the utilization of the router. For example, let's say that the router is receiving A packets per second in total. That means over all the links of the router is receiving a total of A packets every second. Let's say each packet has actually a fixed size, which is L. So the router will be receiving a total of LA bits per second. If the router is receiving A packets per second and every packet has L bits, so LA bits per second is the total traffic that the router is receiving. So the router is receiving LA bits per second, and it can output a maximum of R bits per second. This is the transmission rate. It is receiving LA bits per second, but transmitting R bits per second. So what happens if LA is greater than R? That means the arrival rate is greater than the departure rate, or the router is receiving bits at a faster rate than it can actually transmit. That means that the router will keep the queue, more packets will be added to the queue, and the queuing delay will be higher. Eventually, as we said before, the queue, because it has a fixed size, it will become completely full and there will be no more room for packets and the router will actually start losing packets. This is when packet loss starts to occur. So packet loss occurs when queuing delay becomes significantly high and the buffer is completely full and the router is still receiving packets, it has nowhere to put them, it starts actually dropping packets. So if LA is greater than R, this is the direction you are heading to. Higher queuing delay, higher packet loss. If LA is equal to R, that means you are actually at a dangerous stage. If it becomes less than R, then the queuing delay will decrease. LA is less than R, then the queuing delay will decrease and eventually the queue will be empty and things would be nice. If LA is equal to R, then you are actually on the verge. If it increases a little bit, the queuing delay will actually start to increase. If it decreases, then the queuing delay will actually start to decrease. So at any given time, it is desirable to keep LA less than R. This is actually the main cause of packet loss, that buffers become completely full and the router will have no choice but to throw away packets. This is actually the event of packet loss in this case. Now, when a packet is lost at a router, it is typically up to the end devices to decide what to do. Later in the course, we will actually discuss different types of network protocols. Basically, the network is either going to decide to retransmit the lost packet or it is going to just ignore it and move on. Real-time applications such as voice over IP, typically they can actually sustain a certain degree of packet loss. That means a certain percentage of packets can be lost and a human would not actually notice that the video there is something wrong with it or the sound there's something wrong with it, because packets typically carry only a very small amount of data. So you can lose some of them. But in other applications like email, for example, you cannot even afford to lose a single packet. So if anything is lost, it has to be retransmitted. These are things that we will discuss later in the course. The last metric that we will discuss to calculate network performance is something that is called throughput. Now, we have seen that the router has a certain number associated with it or factor associated with it, which is R, the transmission rate, the rate at which it can send bits out of it per second. Throughput is a metric that is also calculated in bits per second, but it is calculated at the final receiver. This means that throughput is the rate at which data arrives at the receiver. Obviously, this reflects the rate at which data is transferred between sender and receiver. So you might think, if I know R, if I know the rate at which a router is sending, why is it necessary to calculate throughput? Okay. Wouldn't the throughput be equal to R? Now let's consider this scenario. You have actually a device sending data across several routers, and the data is sent or the packets are sent to the final destination. Let's say device A is sending data at R bits per second, and all the routers actually have R bits per second. Now, does this mean that the end device B is going to be receiving data at a rate of R bits per second? The answer is actually no, because the other routers may actually be congested. They may actually be sharing the resources with other clients. And so at the end of the day, even though the total transmission rate of the router is R, this R may actually be shared among different devices. And so at the end of the day, the throughput that B sees is different from the rate at which A is sending. At any case, we calculate throughput only at the receiver. We calculate throughput by calculating the rate at which bits are arriving at the receiver. It gives you a reflection of how much bandwidth you're getting from the overall connection. If you have several routers between A and B, by calculating throughput, you are actually seeing how much bandwidth you are getting from the network as a whole. Not a specific router, not the rate of a specific router, but as a whole. If you have only a single router in the middle that is causing a problem that has high queuing delay and doesn't have sufficient resources, your throughput will actually decrease. There are actually two ways to calculate throughput, either instantaneous throughput or average throughput. Instantaneous throughput is actually as if you have frozen the network and you calculate the throughput at a given instant, at a given point. The average throughput is that you just actually monitor the receiver over, let's say, a whole minute or a whole second or anything, and you calculate how many bits have arrived during this duration. Okay, so we are more concerned with average throughput because it gives you a better image of how the connection is performing. For instantaneous throughput, you might actually be lucky or unlucky to calculate the throughput at a time when queuing delay is low and when the actual rate at which packets are arriving is high. Okay? That doesn't actually mean that over a longer duration, things will be nice. It could be that just at this particular instant, the connection was good. As you know, when you are making, for example, a voice over IP call or a Zoom call, the quality varies. And by varies, it means that sometimes it's good and sometimes it's bad. And so it's better actually to calculate the average throughput over a longer period of time to get a better idea about how the connection is performing overall. And now, just as we did with delay, let's see how we can calculate what is called the end-to-end throughput. That means the throughput between device A and the final receiver B. When it came to delay, we basically calculated all the delay components and just summed them up. We calculated the processing delay, queuing delay, transmission and propagation delays, and the total delay from source to destination is the sum of all the delay components. If you have several routers between source and destination, then you are going to calculate all the delay components at each router independently, and you're going to sum up everything, and this is going to be your end-to-end delay. So what about throughput? What is the throughput between A and B? Is it actually the sum of the throughput between A and the router and B? Is it the average throughput between A and R and B, or what actually is it? The throughput is actually calculated in a very simple way. Imagine that you have two water pipes, one water pipe between A and the router and another water pipe between the router and B. The water pipe between A and the router can carry fluids at a rate of RS bits per second. That means it's a small pipe, it doesn't have a large radius, okay? And so it can only carry fluids at a rate of RS bits per second. The pipe between R and B is a bigger pipe, it has a bigger radius. That means it can actually carry water at a larger rate, or carry fluids at a larger rate of RC bits per second. What is the throughput between A and B? Think about it this way. What will B see at the end of the day? B is connected to R, and R is sending at a rate of RC bits per second. But what is R actually getting? R is getting only RS bits per second. So the question is, can R send something that it doesn't have? The router itself, as we know, doesn't generate data. It can only forward what it's getting from A. And it is getting data from A at a rate of RS bits per second. It cannot actually send anything more than that because it doesn't have it. If I'm getting one packet every second, I cannot send two packets every second. I cannot forward two packets every second because I don't have them. I only have one packet every second. So the maximum rate at which I can send is one packet every second. Same thing here. If R is getting data at a rate of RS bits per second, the maximum that it can send with to B is RS bits per second. Even though it is physically capable of sending at a rate of RC bits per second, but it is not getting this traffic rate from A. So it cannot send what it doesn't have. So at the end of the day, B will only be seeing the rate of RS bits per second. If we switch these two things, if we have the larger pipe at A and the smaller pipe at B, A will be sending to the router at a rate of RS bits per second, but the router will not be able to send at a rate that is anything greater than RC bits per second. So at the end of the day, B will see RC bits per second in this case. In any case, the throughput is actually what is called the bottleneck rate, So if you have a device here sending data to a device in the internet, and you have several routers, you have several links, you see the rate of which link, R1, R2, R3, and R4. You see which rate is the smallest one, and this is your throughput. Okay, so over an entire path, the throughput is defined by the bottleneck link. The slowest link on the path defines the throughput because this is actually the bottleneck. This is the one that is going to determine how much data is going to be sent to the receiver at the end of the day. So the link on the end-to-end path that constrains the end-to-end throughput is the bottleneck link, is actually the average throughput of the path. Okay, if you have a situation like that in the internet, for example, you have several clients here, A, B, and C, for example, sending data to three servers, D, E, and F. Each client is connected to a router R using a link that has rate RC, bits per second, and each server is connected to the same router R with a link that has RS, bits per second. Now, what is the throughput? Is it RC? Is it R? Or is it RS? Again, we follow the rule. The throughput will actually be the bottleneck rate. And so the question is, which one is the slowest? Is it RS? Is it RC? Or is it something dependent on R? The rate of the router is not actually dedicated to any connection. It's shared between the three connections, between A and D, B and E, and C and F. So the rate R is shared. If we have, let's say, 10 connections through the router, then the rate R will be shared among 10 connections. So at the end of the day, we have to ask ourselves, what is actually the smallest rate? Is it RS? Is it RC? Or is it R over 10 in this case? Whichever one is the smallest one will become the bottleneck link and will define the throughput of the path. So we'll stop here. Next time, we'll actually discuss a very, very important topic in our course, which is the topic of the protocol layers or the protocol stack. It is something that, if you understand it well, you'll be able to link all the topics of this course together. So, talk to you next time.